Okay, so good morning. So first of all, I'd like to thank the organizer for the possibility to give a talk. So the title of my talk is Exact Logarithmic Connectivity into the Critical Percolation. It's related to the previous talk, but I'm a physicist, so I will calculate some specific observable and then in percolation with conformal field theory and then check it numerically. So this is what I will do. So this work is based on a paper which has been published on Journal of High Energy Physics. It was my first paper published on Journal of High Energy Physics, but there is nothing about high energy physics here. It's just percolation theory. Okay. So it's done in collaboration with Jacopo Viti, who is a postdoc in Italy. So let me start. So percolation, it's a very simple problem, especially in two dimension, to state. So essentially, we consider a matrix like this, and then we can color the elements of the matrix in different ways. So for instance, in red with probability P, and in blue with probability 1 minus P. And so therefore, in your laptop, it's very easy to draw a picture like this. So this problem seems pretty dull, if you see it, but actually has a lot of structure. So obviously, if this probability of coloring in red certain entries of the matrix is 1, then you will get a red square or red rectangle, any kind of finite domain in the plane. But it turns out that there is a threshold values for P, which is model dependent, so depending whether the percolation problem is formulated on a square lattice, on a triangular lattice, or it's side or bond percolation. There is a finite probability when P, well, actually for P larger than PC, there is a finite probability for a point which is in the bulk to be connected to the boundary of this domain. Namely, by connected, I mean that you see there are next neighboring sites which have the same color, and then I can obviously define a connected component or cluster. Okay, so there's a finite probability at P for P larger than PC for a point to be connected to the boundary, and which means that there is a giant component. There is a finite probability to have a giant component of, here I draw in green, the computer I asked to basically find this giant component, and you will see that, okay, it's present for P larger than PC. So rightly at P equal PC, this cluster, they are fractals. They have fractal dimensions. And, well, this was introduced in the previous talk. They can be studied in many ways. And in particular, in, let's say, very influential work by Langlands, Pouliot, and Saint-Aubin in the 90s, it was put forward a notion of conformal symmetries for the percolation cluster that eventually led to development of SLE, etc. So, I will not discuss from the mathematical point of view, which is this notion of conformal invariance that was discussed before. So I want just to make some few remarks about what is known and what is perhaps less known about the CFT, which describes percolation problem. So, well, essentially, all the critical exponent related to, for instance, as an example, the probability for a point to be connected at the boundary were known since the 80s, essentially. And they were obtained by a combination of heuristic method, like Coulomb gas techniques, and, well, the landmark in conformal field theory, which is paper by Belavin, Polyakov, and Zamolodchikov. Okay, so for an example, probability for a point to be connected to the boundary, so like in the example which I was showing before, it vanishes for p equal pc with an exponent which is 5 over 36. And this you can get from field theory. So there is a way of getting, a heuristic way to get this exponent. What is perhaps, I think, less known, and is actually the crucial point of percolation, I think, is that the free energy is 0. Namely, the partition function is 1. Obviously, there is no any finite size dependence. So from perspective of free energy, percolation is a theory which has 0 free energy, which in the context of the partition function, the sum over the graphs, which is just 1, trivially 1. Yes, this is the usual. Yes. So I will write explicitly later. So the partition function is trivial, but okay, this triviality has a meaning, and the meaning is that actually there is no finite size effect in the partition function. There is no finite size correction to the free energy, which in the language of CFT means that the theory at the critical point at 0 central charge. And this is non-trivial. This is actually the crucial issue of crucial difficulty of percolation. Because if a theory is a field theory at 0 central charge, it means that necessarily either is trivial, but it cannot be trivial because you can calculate correlation function in this theory, or is non-unitary. And if it is non-unitary, then from the point of view of the Virasoro algebra and the presentation of the conformal group, then things start to be extremely subtle. And we will see an example. Okay, so there were, earlier influential work, especially on the two-point function, critical exponent, Paninois, Duplantier, Soler, Dotsenko, Fatiev, etc., that we will also use. Okay, from my perspective, which is somehow, as I said, perspective of a physicist, one of the most remarkable results is due to John Cardy, which kind of was able to connect a problem like percolation, which is purely geometrical, to the concepts which he developed in the context of boundary conformal field theories. So essentially what he was able to do was to actually provide an exact, remarkably exact formula for the probability that such configuration happens, well, at the critical point in percolation. So namely, you consider a percolation problem of a rectangle, and in 2D, critical percolation. When I mean percolation, I mean critical percolation. From now on, I will not specify anymore. Okay, so, and then you ask the question, what is the probability that there is at least one cluster spanning vertically between the horizontal side of this rectangle? And remarkably enough, he was able to provide an exact formula for this complicated observable, which is quite complicated if you think in the lattice model. And the formula which he provided was making use of boundary conformal field theory, namely was able to map this cluster configuration to a 4-point function of a certain operator. And the operator is inserted, is a field theory operator which is inserted at the boundary. So there are at the corners. There are 4 corners, and is a 4-point function, which turns out to be a hypergeometric function where eta is a function of the aspect ratio of this rectangle. And this formula was proven mathematically by Smirnov, I think it was proven in 2009, and then later won the Fields Medal for this. So this is actually a really remarkable result, I think. If you think how it's complicated to get this. But actually in the field theory is very easy. Okay, so another very, I think, perhaps interesting remark was made by Gurari Ludwig. They are 2 physicists again. And about the structure of theories like percolation. So the field theory structure of theories like of problem, which is a simple problem like percolation in 2D. So the remark was the following. So if you consider, for instance, a disk, so a finite domain of the plane, and inside this domain, there is a well-defined percolation problem, and you want to suppose, so S equals 0 CFT, conformal field theory, and you want to study, for instance, correlation of observables which are on the boundary of this domain. Okay. Then correlation of observables which are on the boundary, they are rather special. Because normally you would expect to have, since you are in a CF equals 0 conformal, well, but still you are in a conformal field theory, you would expect to find power law behavior of this correlation function with a critical exponent, which is the scaling dimension of this field. But this turns out to be not the case because of the peculiarity of C equals 0. And actually, what is happening is that if you think in terms of operator product expansion of these two fields at the boundary, well, since they are at the boundary, they are holomorphic, okay? Then the operator product expansion, well, it usually expand over, for instance, the sector which contains the identity, and then it contains the descendant of the identity, etc. Well, if you see this coefficient here, is obviously ill-defined when C is 0. Okay? So they call it C equals 0 catastrophe, this phenomenon. Which in turn implies that the 4-point function of operators which are at the boundary cannot be just, cannot just have usual power law singularities when you do OPE. So the resolution of this paradox that they proposed, Gurari and Ludwig, was that, well, there should exist another field of dimension 2, which is the same dimension of the stress energy tensor, which always appear in this operator product expansion, which comes in pair with this OPE, essentially. There is another OPE with a field with dimension 2, which cancel this pole, which appears at C equals 0, and regularize this OPE. So all in all, what happens is that you generate always logarithmic singularity in the operator product expansions. So the message of these slides is that if you have a theory which is a conformal field theory, but the central charge is 0, like percolation, which seems a trivial observation, well, then the 4-point function of any operators at the boundary, and we will see an example explicitly, it contains logarithmic singularities. Well, there is one possible option which avoids logarithmic singularity is that the case where this operator has dimension 0. Okay? If you can see here, if H is 0, then this is still safe. And that was precisely Cardy example. So Cardy example is a regular hypergeometric, has no any logarithmic singularity. But it's a rather special example. In the example that I will show you, we'll calculate a 4-point function which has a meaning in percolation, and you will see that this logarithmic singularity, they pop up. It's unavoidable. Okay, so let me introduce the main device to calculate objects in percolation theory, which is the Q-Potts model. So it was briefly discussed in the previous talk, but let me write the Hamiltonian. Okay, so the Hamiltonian of this model, it's in 2D, it's it's well known. Well, the Potts model is a simple generalization of the Ising model. So the interaction is ferromagnetic, and delta is Kronecker delta. S of x, they are lattice variables. They can take up to Q colors, and Q for me is always integer. So let me just say that why this model is related, the statistical mechanics model is related to percolation. Well, the reason is easy to see if you perform an high temperature expansion of the partition function. It's a sum over graphs. And these graphs, they come with a measure. The measure is p to the number of occupied bonds, 1 minus p number of empty bonds, times q, the Q is the same as here, so the number of possible colors, to the number of connected components of the graphs, which are called clusters. Okay? So, of course, as you see, if Q is 1, then this partition function is just 1. It's a sum of its binomial theorem, right? And it's percolation, correspond to the percolation problem. If Q is not 1, but for instance 2, this is the high temperature expansion of the Ising model. These are called the FK cluster, which are used in Monte Carlo simulation, the Svensson-Wang algorithm, for instance, for Q equal 2. For Q equal 3 and Q equal 4, you have other type of random processes which are labeled by this integer. If Q is larger than 4, then the Potts model undergoes first order phase transition, so there is no anymore a conformal field theory. Well, unobvious, let's say. There are conjecture, I think, recently, by Richkov, I think. But there is no unobvious description for Q larger than 4 than this problem in conformal field theory. So I will not consider Q larger than 4. Actually, I will focus on Q equal 1, which is the case of interest for percolation, and then give some result for Q equal 2 and 3, and 4 also. Okay, so what are the observables that I'm going to calculate? So suppose that we have some random process inside this finite domain of the plane. So the observable which I want to calculate, they are connectivities. So namely, they are probabilities that they have some certain set of points at the boundary, and they are connected together. So for instance, if I have 4 points at the boundary, I can ask the question, what is the probability that there is a cluster which connects all of the 4? Or what is the probability with the measure which I showed you before? What is the probability that, for instance, the points 1 and 2, they are in the same cluster, and 3 and 4, they are in another cluster, but the 2 are different, etc. Okay? So all in all, if you count with 4 points, all in all, with 4 points, you have 14 possible choices of partitioning the points on the boundary. But not all of these 14 possibilities, they are linearly independent, obviously, because, for instance, the sum of the probability has to be 1. So they are not linearly independent function. It's not. So this vector space of function, you have to find the right basis. And it turns out that the right basis, so the number, there are a lot of sum rules, actually. You can reduce this configuration to less points, for instance. So the probability of 4 points summing over 1, you can reduce to 3, etc. So it turns out that actually the convenient basis for the connectivities, for instance, for 4-point connectivities, or actually n-point connectivities, is in correspondence with the non-single, non-crossing partition, which means the following things. It means that basically the basis you choose in such a way that you can never disconnect one point from all the other. So for instance, if n is 4, there are only 3 linearly independent functions, which are given by probability that 1 is connected with 2 and 3 with 4, 1 with 4 and 2 with 3, and all together. So you see that you can never disconnect one from the other. Okay? So this is the convenient basis for, which means that, for instance, if you want to have probability that 1 stays alone and 2, 3, and 4, they are in the same cluster, well, this will be equivalent. This will be essentially proportional to a 3-point connectivity. So it's not a 4-point function, basically. Okay? So these are the 3 linearly independent objects. So in this talk, before going to the detail, I will tell you the result. So what I have calculated. So actually, I calculated all the possible ratios of these 3 functions. Ratios, they are adimensional, so they are easier to calculate. They're meaningful, actually, to calculate in field theory and compare with lattice simulations. Okay? So I calculate ratios of these 3 functions, essentially. And in particular, one which is convenient is the ratio between the probability that in the percolation problem, for instance, this one is connected, the central one, so 1 is connected with 4 and 2 is connected with 3, divided by the sum of all three probabilities. It's a normalization. So here is the result. This is the analytic result. So as you see, I call it R, this function. In principle, function of 4 variables, the position of the points at the boundary, x1, x2, x3, and x4, but by conformal symmetry, it's a function only of their cross ratio. So it's actually a function of one variable, which is eta. I call it eta. Okay? By the way, you can see that by conformal mapping, again, since you have 4 points on the boundary, right? The point x1, you can map it to 0 on the real axis. The point x2, the point x3, you can map it to 1. The point x4, you can map to infinity. So eta, which is the mapping of x2, is in between 0 and 1. So this function, it's enough to plot it from, well, actually to calculate it from 0 and 1 because of the ordering at the boundary. Okay? And of course, it's a probability, so it has to be positive and from 0 and 1, and well, it's fine. Everything is sort of fine. Well, these trivial checks. Then we will see the numerics, how it compares. So these are the results for Q equal 1 percolation, Q equal 2 Ising, 3 for Potts model, 4 state Potts model, etc. And it's also interesting to observe that since it is a ratio, it is not only conformally covariant, but it's conformally invariant, which means that you can do simulation of triangular lattice, apply Schwarz-Christoffel transformation, then compare with this result here. And this is what we will do. So simulations are done in a triangular lattice because it's easier. The finite size effect, they are less pronounced on a triangular lattice. Okay, so this is this final statement essentially. And now I'm going into some detail for the calculation. So some details of conformal field theory, and then see how I was able to calculate this ratio. Okay, so basically the conformal field theory, which describes the Q-state Potts model, was known since long by work by Dotsenko and Fatiev in the 80s, essentially. So they were the first to identify the central charge, how the central charge of the conformal field theory is related to Q, where Q is the number of states in the Q-core Potts model. And then from this, we're able to identify the scaling dimension of the operators, etc. So essentially, the central charge of the conformal field theory is related to the parameter Q. So the central charge I hope that you know what is the central charge, but somehow, if you don't know what is the central charge of a conformal field theory, then you can think the central charge is a certain parameter which identify the model, essentially. It's like a fingerprint of the quantum field theory. Okay, so it was parameterized. They parameterized the central charge like this, so 1 minus 6p times p plus 1, and Q is related to this parameter p by this formula. So you see that if p is 3, actually I think if p is 2, if p is 2, then q is 1, and c is 0. So if p is 3, q is 4, q is 2, and c is 1/2, etc. Okay, so so this was the first piece of analytical information. So there is a mapping between the central charge, we described the CFT, and Q. Then the other piece, very important piece of analytical information was provided again by John Cardy in the 90s, when he pointed out that the operator that you can insert at the boundary, so here is like, the problem is like this, so you have a certain domain, and here it's boundary, and you want to introduce a certain operator at the boundary of this domain. We call this operator phi of x. Okay. So in a CFT, the operator that you can insert at the boundary, they are constrained. cannot be any kind of operator. So in particular, it has to have a very specific scaling dimension. And the scaling dimension is parameterized like this. It's a chiral operator, which means that it's holomorphic. So in 2D, this is actually a function, holomorphic function of Z. And this is, if it is the complex plane of Z. Okay. So, and its conformal dimension, they are parameterized like this, where P is the same P as here, and R and S, they are integer. So for instance, if you take C equal 1/2, the Ising model, then you can recognize that H, the conformal dimension of a field with integer 2 and 1, H21 is 1/2, which correspond to insertion at the boundary of sigma, the spin field, etc. Well, in principle, you could imagine to give an interpretation to all of these numbers in what is called the so-called Katz table of the conformal dimension, but up to now, it is not known. They are not known. So only a very tiny subset of this infinite grid of conformal dimensions as a well-defined meaning in a geometrical or statistical mechanics problem. Sorry? And now I'm coming, I will show you. Apart from some, and in particular, the one which are on the first column. This is an example that you discovered, by the way. So this operator here, which are on the first column, they are peculiar because they are responsible for insertion of clusters at the boundary. So in particular, if I consider in this notation by Katz, the operator phi 1, 2s plus 1, and I insert this operator at the boundary, then what is happening is that essentially this operator enter S cluster at the boundary. And the exponent H1, 2s plus 1, they are also called watermelon exponent for a reason which I think is clear if you imagine to have a two-point function of these operators. Okay? So, in particular then, if you see, for instance, if you are in the Ising model, you want to insert, this is a heuristic, of course, but it has a meaning. It is all consistent. So if you are in the Ising model and you want to insert one cluster at the boundary, then the operator which does this is the field phi 1, 3 with dimension 1/2. If you want to insert two clusters at the boundary, then the operator which does this is phi 1, 5, which has dimension 5/2, etc. And then you go on. And the OPA is consistent with this identification of clusters. Yes. Yes. Yes, yes. If you want to go to look at the geometrical problem, yes, you need to include an infinite number of operators. Yes. Otherwise, they don't have a real meaning in terms of this table if they do not fit. You can also have operators that do not fit with this table. They are even more complicated, and they enter in the bar case. So it's even more complicated. It's not even known now, completely known up to now, I think. Okay, so now, once you understood that I need to consider the 4-point function of the operator phi 1, 3 to get for let's say, connectivity of 4 points, then, okay, it's rather clear that even geometrically, what is happening is that I can connect these 4 points in 3 ways. So this 4-point function, they should expand as a linear combination of the 3 linearly independent connectivities that I showed you before. So it's when I calculate this object, I know that, well, it should be part of a vector space of dimension 3. 3, linearly independent connectivities. And then I also know, and this is why it is self-consistent, that the 4-point function of the operator phi 1, 3 Well, it solves actually a linear differential equation of degree 3. So I know that these solutions, they span a vector space of dimension 3. Right? And this 4-point function, this comes, it's subtle. I mean, it's the fact that it solves a linear differential equation of degree 3, it follows from BPZ. The fact that you can assume it is rather subtle because the theory is not unitary in principle, but is self-consistent. It was proven by Gurari and Ludwig. Okay, so it solves a linear differential equation of degree 3, which I can calculate it on the upper half plane and then map it wherever I want by conformal mapping. So the structure, so Z is on the real axis essentially now, okay? Because the points are on the boundary. So this 4-point function is usually parameterized by a prefactor, which has certain dimension. And then a function which is dimensionless, which, okay, here I call it conformal block. This is actually a function which encodes the algebraic structure of the CFT. So it's like, you know, some spherical harmonics in the angular momentum. So it encodes a certain representation of the conformal group, which is associated to this 4-point function. Okay? So, well, now the recipe is the following. So this is the third-order linear differential equation, which is solved by the function g. So there is a well-defined prescription to write this linear differential equation. So now the game is the following. On one side, we have a basis, which is the basis of geometrical objects, which are these linearly independent connectivities. On the other side, we have another basis, which is the basis of solution of this differential equation. And this linear differential, in this solution, they are conveniently written in terms of conformal blocks, which are the algebraic object, which are solution of the differential equation. So the game is to try to change the basis. To go from this basis, the solution of the linear differential equation in terms of the blocks, to the geometrical basis. Okay? So in this you can do in a certain partially rigorous, partially heuristic way. Okay, so the blocks, they are parameterized by a rational number rho, so the solution essentially of the linear differential equation. They are parameterized by a rational number rho, which is the solution of the initial equation. So as you see, this rho can have 3 values, if you look at, and the values are 0, h13, this is the initial equation, h13 and h15. And of course, this is consistent with the OPE structure, because here you have two, you have like 2 field phi13, which produces 1 cluster, and you want to glue them together. So what you can generate, there are configurations where at most you have 2 clusters. Okay? So at most you can generate the field H15, phi15, with dimension H15. Okay? So, well, then we need to understand what these numerator and denominators are in terms of the solution of the linear differential equation. And this we can do in a certain heuristic way by looking at limits. Basically, as also Cardy did in his famous paper. So the idea is simple for the numerator. For numerator, it's really rather easy to understand what is happening. Because the numerator is probability that 1 is connected with 4 and 2 is connected with 3. But in all the process, they are disconnected from each other. So when you fuse together, so you bring x1 and x2 close together, well, you generate configuration where you have 2 clusters meeting at that point. And since this is related to the insertion of phi15, well, it means that this numerator here is exactly the conformal block of the field phi15. There is no other option because it's the largest possible dimensions. So the numerator is easy to identify. It's directly related to a solution of the differential equation, the one where the index rho is h15. There is no other option. For the denominator, it's more complicated, but you can deal because you can use the Kramers-Vanier duality. So the Kramers-Vanier duality maps this combination of connectivity to a single partition function. So it's no more a sum. That's why I use this denominator. But just one single partition function on the dual lattice, etc., where you have fixed boundary condition for the Potts variables on the boundary. So they have color alpha, then color beta, then color alpha, and then color beta again. So this you can prove it by duality. There is a duality transformation. And under the duality transformation, the field phi 1, 3 becomes the field which create this discontinuity in the boundary condition from alpha to beta. Right? This is already present, was already observed by Cardy. So when you consider the limit in which x1 goes to x2 now, you can see that, well, you can never get any more a field of type phi alpha beta, because the boundary condition, they are homogeneous after the fusion. Okay? So you have to exclude in this combination the conformal block of phi 1, 3. It's the only thing that you can say. So this is actually a symmetric combination under the exchange of x1 and x3 of the block of phi 1, 5 and identity. So phi 1, 3 cannot appear, is the only thing that you can say, and it has to be symmetric. But it turns out that there is only one symmetric solution of the symmetric in the exchange of x1 and x3 of the differential equation which has this property. So in this way, I can fix uniquely this ratio up to a constant, and the constant you can fix it requiring that r for eta equal 1 is 1, because it's dominated by this. Okay. So now come to the result. So I give some formulas. So for instance, these are all explicit. So for instance, the ratio R at Q equal 1 in terms of the harmonic of the cross ratio is given by ratio of these two blocks. I call it G2 and G0. So these blocks actually can be expressed, also the denominator actually, they can be expressed in terms of hypergeometric F32, but it's a rather involved expression, so I don't write it because it's kind of useless to write it here. But they are known in terms of function F32. Okay? Actually, there is a software by a mathematician, I think in Florida, which is pretty remarkable. So this software solves a given linear differential equation in terms of hypergeometrics. So it's able to find non-rational substitution which reduce, if it exists, an hypergeometric solution. Exactly, solution of linear differential equation to hypergeometric solution. So I asked this mathematician to run his code and provide some complicated hypergeometric, but then we have to massage it because they are not well defined in all the complex plane, etc. But this was the way in which get this F32. Okay, so now, but of course you can do also series expansion. And then the series expansion with Mathematica, you can go to very, very large order. Eta to, I don't know, 10,000. Even more. Okay? And then, okay, so you see that the denominator of this function, the denominator G0 has a logarithmic singularity, as expected. So here it's actually first example where in a true connectivity, you can get a logarithmic singularity. So this is for eta going to 0, when the anharmonic ratio goes to 0. And the coefficient of this logarithmic singularity is turns out to produce a b. If you remember one of the first slides when I wrote the argument by Gurari and Ludwig, the b which parameterizes the logarithmic singularity is minus 5 over 8, which again is consistent with what Gurari and Ludwig they claimed long ago. Okay, so this is the Monte Carlo, and here it's the prediction with the CFT, which you cannot see because it's perfect. So it's below. Okay? So this simulation, they are done on a triangular lattice. So you can see that agreement between theory and Monte Carlo, it's perfect. Of course, I cannot prove it, that is exact, but I believe that is an exact formula. So this is eta, which is the cross ratio between the 4 points at the boundary. And R is this particular ratio of connectivities. Probability that 1 is connected with 4, 2 with 3, divided by 1 with 4, 2 with 3, 1 with 2, 3 with 4, and all together. So it's a ratio of connectivities. Yes. Sorry. Yes. Yes. No, I think it is dominated by this 1, actually. G0 here, this denominator. It's a subleading singularity. Unfortunately, it's not, G2 goes to 0 like eta square. So unfortunately, it's not the leading singularity. Yes. Okay, so this is for percolation, and this is another interesting numerics. So for percolation, one is also able to do some extrapolation for the value when the anharmonic ratio is 1/2. And the agreement with the field theory is on the 5th digit. So it's quite a remarkable also this fact. I mean, it's not easy to find an agreement between field theory and experiment which is on the 5th digit. I think if you push these numerics, then percolation will provide perhaps the best, I think, my guess, the best agreement between field theory and real experiment. This is on a triangular lattice. This is on the triangular lattice. But it doesn't matter because you can use conformal symmetry, right, to map it anywhere you want. But, yes. But the simulation here, they are done on a triangular lattice. And then one uses a Schwarz-Christoffel transformation too. Okay, so now this is for Ising. For Ising, there is even a more explicit expression for this ratio. It's an integral, again, using this magic code by this mathematician in Florida, which is remarkable. So for Ising, apart from the power series, you can get also an expression for the ratio, which is an integral of an elliptic integral. So there is an even more explicit and simpler expression with respect to percolation. So now here are 4 points on the boundary for Ising, for the FK cluster of Ising, but the same problem. And the function is simpler. So perhaps it's easier to understand what is the meaning of this function mathematically. There is a logarithmic singularity also here, but when eta goes to 1 now. So around here, this function develops a logarithmic singularity, which you can interpret it algebraically in terms of representation of Virasoro algebra, but it's quite complicated. Okay, so now these are q equal 3 and q equal 4. So for q equal 3, the agreement is similar. Essentially, this is a very explicit formula. For q equal 3, it trivializes essentially. And q equal 4, well, trivializes is not easy, but somehow there is this solution of the differential equation that becomes essentially polynomial. And also for q equal 4, they are polynomials. But for q equal 4, you see that the numerics is not that great. There is a certain discrepancy that you can also see from the errors. So here it's the relative error for percolation. Is in all the domain 0, 1 of eta, so it basically goes to 0 very fast. For Ising goes to 0, for q equal 3 goes to 0. But for q equal 4, this relative, well, the absolute error is still about quite small, but The relative error, it seems to go to 0, well, if you have a big imagination. So it doesn't seem really to. But the reason is that for Q equal 4 is very subtle numerically, because for Q equal 4, typically for Q four-state Potts model, you have to introduce logarithmic correction to the scaling. And this logarithmic correction to the scaling, they are very subtle. And for this problem, they are not known. So essentially what you can see is that if you plot the analytical value minus the Monte Carlo, so sort of the L infinity norm, if you want, okay? So which is somehow a correct norm for convergence in some space of function. Well, then you can see that this for different values of L, these are different values of L. So you can see that it goes to 0, but very, very slowly. And when you fit it with some power law, with some logarithmic correction, then it's compatible with 0. So this is the area of confidence of the fit. So I think here the subtlety is that actually there are logarithmic correction to the scaling, and this logarithmic correction to the scaling, they sort of, for the four-state Potts model, they produce this very, very slow convergence to the theoretical analytical value. Okay, so I think I'm done. What time is it? Okay, yeah, so I'm perfect. I have to. Well, if you want just to mention a few conclusions. Yes.